Hello and welcome to this Manufacturing Systems Technology Part 2 Module 7. In the last module we had talked in a major way about quality loss and how that could be used to take important management decisions. We did two different case studies, where in one case study we tried to select between two products based on the ultimate shear strength of a bolt which would otherwise support a rotor system. The other case was related to the shifting of the point of gear changing in an automatic transmission, where the comfort zone of the operator, the truck driver, was taken into account for designing the factory tolerance. So both of them were illustrations where quality loss was used as a basis for selection of the right strategy, management strategy, which would be applied to that condition. Today we are going to discuss a little more of this robust design approach, particularly of products and processes, and how at a systemic level these different quality issues related to engineered systems can be studied. So, and how robustness can be introduced into the picture by design, by process optimization, so on and so forth. So robust design is an approach concerned with designing a product or process that emphasizes the reduction in performance variation through the use of design techniques that reduce sensitivity to the sources of the variation. Okay. So here is an engineered system, for example, which is shown, and there are different factors as can be seen applied to these engineering system. So the input factor is also known as the signal factor, which is by and large dependent on the user of the system, and because of the signal factor, the engineering system gives a response or an output, okay, of a particular type which the engineered system is supposed to give. So monitoring the level of the output or variability in the output level is of significant concern while designing the system, and obviously the response value as well as the variation would get influenced heavily by means of the noise factors, okay, which are probably beyond the control. They are uncontrollable, and for example, change in temperature, change in humidity, these kind of things, if the process is set up in a particular manner, it's something that you can't really do much about it. Or control factors, where by changing certain control aspects related to the engineered system, we can in a way be able to vary the response level. At least the output and the variation part can be substantially altered, okay, based on these control factors. So simply stating, we want to achieve a target quality characteristic, but at the same time we want to minimize the variation in the product's functional characteristics, and that's typically because we wanted to have a minimum quality loss associated with this particular product. And the target and the variance of the product's quality characteristics are by and large affected by the variables which are classified as controllable factors and uncontrollable factors. And uncontrollable factors are these noise factors, as have been illustrated, and controllable factors can be many, as I will probably illustrate in more details later on. It can be related to the user, or it can be related to even the designer's choice of certain factors associated in the designing of the product. So let's look at the controllable factors. What are really controllable factors? They are sort of factors which can be easily controlled, such as choice of materials, for example. Let's say the mold temperature, the cutting speed on a machine tool. These are some things which are really in direct control of the operator, or in direct control of even to some extent the designer, okay, who designs the process range, for example, of operation, okay, things like that. So by and large the controllable factors are twofolds. So I'll just write this down here. So the controllable factors can be really classified into those factors which are directly controlled by the user or the operator of the product, okay, and there are then factors controlled by the designer. We will try to understand all the engineering systems by by sort of taking specific example cases where we can find out which are those which are controlled, which are those factors which can be controlled easily by the user, the operator, and which are the factors really which are in the ambit of the product designer as such. So, for example, let us say when we look at any engineering system, as I told you, there is something called a signal factor, which is the input response to the system that has been given by a user or an operator for the system. And obviously, because of this input response, there is a output response which is generated, also known as the response, better known as the response. And the question is about controlling the level of that response or the variability in the output level of that response, given the signal factor. And so there are many controllable and noise factors which are associated in that process which would do all this. But the principal generator of this signal which would be associated with the functionability of the engineered system is the user itself or the operator itself. So, the signal factors obviously are the controllable factors, right, and the intent that the signal factor really has is to attain a certain target performance or to express the intended output in some measurable form, with some variability of an engineered system. So, let us look at an example. For example, you are a car driver and you want to turn the car to a certain direction. So, obviously, you will turn the steering wheel, and the steering wheel is basically the signal factor which you are sending into the system, which is creating the car or which is enabling the car to take a right turn. So, obviously, the angle which you have to move your steering vis-a-vis the angle that the car really moves are quite different, okay. And therefore, there is something called a gain of or an amplification of the signal factor, finally resulting in an output response of the system, etc. So, if I were to understand this as an engineering system, we will see that the signal factor here is the angular twist or turn of the steering wheel generated by the user, and the response of the system is actually the amount of degrees that the car is able to bend its track from moving rectilinearly, okay. So, that is how you can gauge what is the controllable signal factor in the more in the domain of the operators or the users. There can be other examples of signal factors. For example, in a refrigerator, if you were to take the control, the temperature control knob to a certain level of temperature, and obviously there is going to be a fall of temperature based on whatever set values that you have incorporated. So, the signal that you are generating is that turning of the knob which is actually setting the value to a certain level, and the output of the refrigerator of course is the time that it would, in some time it would come to that particular temperature value. That is the response of the system based on the signal that you are generating in terms of turning the knob. Similarly, there are other things like, for example, in remote control, when you try to change the volume or the brightness of a television, you are basically generating the signal from the remote control, and it is actually resulting in the influence on the screen, okay, in terms of the volume increase or in terms of the brightness or contrast change associated with this signal factor that you are generating through the remote. So, any engineering system, for example, can be studied in terms of the user generated, the operator generated signal factor, and the response or the output of that system. So, this is the first principle that you should follow in order to realize any engineering system for giving a systemic point of view to the quality of output of or the performance of the system. So, let us look at the factors which are controlled by designers. We already did a very detailed analysis of the factors which are controlled by the operator or the user directly. So, there are principally three different types of such factors which fall in this category. One is called the variability control factor. Okay, so, they affect the variability in the response, and you can simply call them control factors or you can call them variability control factors. For example, in a control circuit having a transistor, and also the circuit is intended for transistor as an amplifier. So, if you increase or decrease the gain voltage, the output response of the transistor is also going to be changed accordingly. Okay, so, the voltage, if supposing the gain factor is increased, then the output voltage or the response would go high, and it will scan over a different range, and vice versa. Okay. So this is called a variability control factor. So the output range of the voltages that can be achieved of the transistor is simply higher if the gain voltage in this particular case is high, and vice versa. If the gain voltage is lower, then the output range which gets sort of initiated, or under which the transistor is bound to operate, that range reduces. And I'm going to illustrate this a little more closely in one of the next examples that particularly Taguchi talks about, when he changes the gain and sees what is the variability in the response. The other important factor which is in the control of the designers are called the target control factors, and these are so-called factors which can be easily adjusted to achieve the desired functional relationship between the user input signal and the response. For example, let's go back to the case of the steering wheel and the customer who is a driver of a car. Now, if he actually turns the steering wheel by angle theta, obviously the amount of angular turn or bend of the car would be very pertinent, and the designer can give a additional factor within by giving a gear ratio, where the steering mechanism of an automobile with a certain gear ratio may amplify the signal given by the operator, which is a certain angular twist in the steering wheel in terms of the overall angle that the car executes. Okay. So that gear ratio, which is about the way that the rack pinion assembly would move, which would enable the car to steer right or steer left based on the angular rotation of the steering wheel. This is again a designer's control domain, and the designer can give a very sensitive steering by having a commensurate gear ratio or vice versa. So this is again target control factor. So once you have controlled the variability level by giving a range, you also control how quickly the output response of an engineering system achieves a certain particular level, as in the case of car steering you already saw it. It's called the target control factor. And finally, there are certain other factors which the designer has, which are also known as neutral factors. And why they are called neutral is that they do not really affect either the mean response or the variability in the response. Okay. So either the output level is not influenced, or even the variability of the output level also is not influenced in these particular cases. So they are known as neutral factors. And obviously it is important to know these neutral factors, since you may basically change the levels of those factors to do an overall cost saving. Unknowingly in the design you may put something which is not really related to the output level or the variability of the output level, but still it exists in the design because of some other reasons. The reasons could be related to, for example, over designing of the products unknowingly because of the iterative process through which the design is carried out. And if such factors can be isolated and such factors can be eliminated, it may obviously lead overall to some kind of a cost saving, and can help the product to operate at the most economical level. Okay, so those are the neutral factors. So we will try to identify some of these factors in a realistic sense probably in the next lecture, where I'll give you an example of a transistor gain or a transistor circuit, and I'll show you that how you can change really the target control factors and the variable control factors in such a circuit. As of now, we'd like to conclude this module. Thank you.